Hello everybody and welcome to my shop. In this video we're going to go over encoders, more specifically incremental encoders. We're going to take one apart so we can see how it works, and then I'll explain what we need to do in our code to be able to use the encoder. When I first started using encoders, I found that we can write code to get it to work, but it's not very reliable. Then there's other ways that I have found that are very reliable, so we'll discuss what's worked the best for me in the past. Then we're going to use an encoder to turn the brightness of an LED up and down. We're also going to write to the serial monitor whether we're going clockwise or we're going counterclockwise. After all, that's exactly how we determine whether we should be going brighter or dimmer. Let's get started. I was going to discuss both absolute and incremental encoders in this video, but to be honest, I don't think I've ever used an absolute encoder with my hobby stuff before. I wanted to kind of stick with what I've used before, and I'm thinking people like yourself with similar hobbies will use the same. With that in mind, that's why we're going to stick with incremental encoders today. So I do want to discuss briefly that there are two big differences between the two. The absolute encoder here, when you turn the power off, you reset the power and it comes back on, it'll know right where it left off. It knows its current position. Whereas the incremental encoder does not. It loses its position. So with that in mind, that's also why there's a cost difference. The incremental encoder will be a lot cheaper. There are, of course, workarounds. When you turn the power back on, you can set up like a home routine so that it has to find home and then resets the count and starts from there. But that's just something to keep in mind. So we have here an incremental encoder that I've used several times in the past. You can get these pretty cheap on Amazon. I think last time I bought some, I got like 5 of them for about $10, $15. So I've taken one of these apart so that we can get a better understanding of what's going on here. It's got a little clip. We just pry that off. We can remove the shaft and flip it upside down here, and you can see that it's almost got like a wheel of contacts. So as we spin that wheel, they're going to turn around. As those are turning, they're going to make contact with these contacts here. So one of these sets, and I'm not sure exactly which one, I'd have to look at the circuit board closer, but one of these is going to be pin A for the clock, and the other one is going to be pin B for the data. So when you press this shaft down, it actually operates the switch. That switch is going to push this contact and make contact with what's underneath it. So we have our ground VCC, we have a switch pin, we also have a data pin and a clock pin. I went ahead and made this on the laser so that I could show you a little easier of what's going on with the encoder and how it works. So we have here pin A for the clock pin and pin B for the data pin. Now on the real one, clock and data are side by side, so one is over here and the other one is here. But the timing that the contact is made and goes high or low is going to be the same. This is just going to be much easier for me to show what's going on. So I'm going to go ahead and put this piece in here so I can turn this a little easier. We're going to bring up a digital square wave to show you when each contact is going high or low. So as we're going clockwise, pin A would go high, then pin B would go high, then a half a cycle later pin A would go low, half a cycle later pin B would go low. The same thing would happen again. Pin A would go high, pin A goes low, pin A goes high, pin B goes high, pin A goes low, pin B goes low. And this keeps going as long as we're going in a clockwise manner. So if we go counterclockwise, that's actually reverse. So we can look at it kind of from the other side of the square wave here. Pin B is going to go high, then pin A is going to go high, then pin B is going to go low, then pin A is going to go low. Then the same thing is going to happen again with the next cycle. Pin B's high, pin A's high, pin B's low, pin A's low. And it keeps going. So this information is going to help us determine whether we are actually going clockwise or counterclockwise in our code.
Alright, let's go ahead and take a look at our code. So we're going to start at the top with our little title block here. That's going to say the name of the sketch, who made it, date, and the purpose. In this case, it's Encoder Basics. And myself, Sean, at Dad Makes for Hobbies. And the date and the purpose of the sketch is we're going to use a rotary encoder to increase or decrease the count or the number, and we're going to display that to the serial monitor. That's going to help us show whether writing the code this way is accurate or not. So let's go ahead and get started. We're going to create a couple of constant of type byte. So the first one here is going to be the clock pin of the encoder, and we're going to plug that into the pin number 3 of the Arduino. We're going to call this pin A. We're going to call the next one pin B. That's going to be plugged into pin 4 of the Arduino, and that is going to be the data pin of the encoder. Next one is a constant of type byte. For the switch pin, we're going to plug that into in the Arduino's pin 5. Now we need a couple different variables. First of all, we need a encoder position. So we need to use this to store the number that represents the position of the encoder. We're going to start that at 0. We also need to keep track of the current state of pin A, or the clock pin, and the previous state of pin A, or the clock pin. So we're going to create a variable of integer for both of those, and we're going to start them out at 0. In our setup, we're just going to start the serial monitor, and we need to call pin mode to let it know that pin A and B are going to be used as inputs. And our switch pin is also going to be used as an input, but we're going to use the pull-up on this one. So in our loop function, our main purpose here is we're going to keep looping through this, and we're going to try to find out when the encoder is turning, when it's changing states. When it does change states, we need to compare it against pin B, our data pin. So the first thing we're going to do is we're going to take a digital read of pin A, our clock pin, and we're going to store that in our current state variable. Then we're going to jump into this if statement where we're going to say if our current state is not equal to the previous state. This is going to tell us if it is not equal to the previous state, then we know it's moving. If they were equal, like they were both 0, then we know the encoder is not moving. Let's take a look at the digital square wave that we saw before. This is the output of our encoder. So if you remember, when we were turning clockwise, our pin A would go high first, and then our pin B would go high, then our pin A would go low, and our pin B would go low. What we're doing in our program here is we are looking for pin A to change its state. So if it goes from low to high or from high to low, whenever it does, we need to compare it to pin B. So if we're going clockwise and our pin A changes states, it goes from low to high, we look at B, B is low. Now as we continue to rotate clockwise, our pin A is going to go change states again from high to low, so we look at B, and B is high. So there's kind of a pattern you're seeing here. If pin A is high, pin B is going to be low. If pin A is low, pin B is going to be high. They're always the opposite of each other when we're going clockwise. So now let's take a look at what happens when we go counterclockwise. If you remember from before, when we're going counterclockwise, our pin B is always going to go high first, then A, then pin B will go low, then pin A will go low. So we can just look at it from the right side of it here. So we're going to take a look at pin A again. We're going to take a look at our clock pin when it changes states. When it does change states, it goes from low to high. We're going to take a look at B. B is high. We keep rotating counterclockwise. We change states on our clock pin again, pin A. When it goes from high to low, then we look at B. B is low. Again, there's a pattern. Whenever A is high, B is high. When A is low, B is low. That's how we know we're going counterclockwise. So in our code, our first if statement, we're going to see if we're moving or not, if we're rotating. Our second if statement, if we are rotating, we're going to take our current state, we're going to do a digital read of pin B, and we're going to see if it is not equal to the current state. That means we're going clockwise, and we're going to add to the encoder. If it is equal to the current state, then that means we're going counterclockwise and we're going to take away from our encoder position. Then we're going to come down here and we're just going to go and write that to the serial monitor. And then we're going to record our current state in the previous state so that every time we loop through, we can compare it again to see if we're moving.
Alright, let's go over how we've got this wired up. A few things we're going to need. We need our breadboard, our Arduino, our incremental rotary encoder, and our LED, and some jumper wires. So to get this all put together here, I'll put a schematic up on the screen. We're going to start out going from our Arduino. We're going to bring power over to the power rail. Our positive 5 volt and our ground will go to the power rail. Then from the power rail, we're going to take our VCC or 5 volt over to the rotary encoder, and we're going to take our ground over to the ground pin. Next, we're going to go ahead and use this green wire here. That's going to go from our clock pin, or our pin A. We're going to run that up to pin number 3 of the Arduino. Then the yellow pin, or the yellow wire, we're going to go from our data pin. That's going to go to pin number 4 of Arduino. Orange pin is going to be for our switch. We're going to go from the switch pin of the encoder over to pin number 5 of the Arduino, and then from pin 6 of the Arduino we're going to run that over to the anode of the LED, or the positive side. From the negative side we're going to run a jumper wire over to ground of the power rail again.
Okay, I'm going to go ahead and verify and upload to the Arduino. Now I get a little bit of garbage that shows up on our serial monitor down here. I'm just going to go ahead and clear that. And I'm going to turn to the right or clockwise position. And we're working. Oh, right there it jumped from 6 to 7, 8, 7, 8, 9. So it did jump around a little bit there. Let's clear it again. Whoa, one click and it did 10, 9, 10, 9, 10, 9, 10, 11. But then it continued on with 12, 13. So it works, but not quite what I'm after. I'm looking for a little bit more accuracy. Okay, with that being said, let's go ahead and make some changes to our code that's going to make it a lot more accurate and consistent. I'm going to go ahead and type it up, and we'll speed the camera along, and then I'll go through and describe everything I've done. Okay, now that we've made some upgrades to our sketch, let's go ahead and go over the changes real quick. So most of this is the same. I don't remember if we actually called out the constant of type byte for LED pin 6 before or not, but we've added that to this one because we are hooking up our LED on this one. We've already wired it in. So it will be going to pin 6 on the Arduino, and it does need to be on a pin that has pulse width modulation, or PWM. We have a couple unsigned long variables, previous millis, current millis. We're going to set both of those to 0. We're also going to set a millis delay time to 5 milliseconds. And I'll go over that more in detail here in a minute. We still have our encoder position that we're going to set to 0 initially. But now instead of using a current state and previous state, we're doing this a little bit different now. We're going to be using an interrupt. So we're going to use a previous encoder position and an encoder position to know whether or not we've changed. We're also going to make an adjustment to the sketch to allow for a high and a low limit on our encoder. So we're adjusting an LED up and down. If we go all the way down to 0, it's off. We don't need to go into the negatives. And we can only make it so bright. So I'm going to set it for 40 initially, so we can turn it up to 40, and that should be the brightest it's going to get. We're also going to have a string variable. We're going to put in that variable a CW if we're going clockwise, or a CCW if we're going counterclockwise. We get down into setup, and this first line in setup, we're going to attach an interrupt. That's the biggest difference between this version and the previous version of our sketch. So you might want to Google attach interrupt and go straight to the Arduino site. You can get a lot of information on this, but the main things to keep in mind is on the mode, there's several different modes we can use. I've used all of these. I've tried falling, rising, changed. I keep going back to low because low seems to work the best for me for some reason. If you have any idea why that is or what I'm doing wrong, leave a comment down below. I'd love to learn what the difference is, but I keep having to use low. That one works consistently. The ISR, the Internet Service Routine, that's basically a function that we're going to write that is activated when the Arduino sees pin A go low. So another thing to keep in mind is the pins that are allowed to be used for interrupts are different on the Arduinos. So I'm using an Arduino Uno, so I can use pin 2 or 3. So that is why pin A on our code is set to pin 3 as our interrupt. So our first line of code here in this setup is going to be, we're going to attach an interrupt. We're going to do a digital pin to interrupt. That's pin A. When this is activated, it's going to run a function that we're going to write called have rotation, and it's looking for low. So it's going to keep looking at pin A, and when it sees pin A go low, then it's going to run this other function down here that we're going to create called have rotation. And then the rest of the items in our setup, we're going to go ahead and start the serial monitor. We're going to do some pin mode for pin B, input, switch pin, input, doing the pull up. We are adding a pin mode for the LED pin. Going to make sure that's an output. Then we're going to go into our loop. So our first line in the loop, we are basically taking a snapshot of the current time. So current millis is going to equal to the results of running the function millis. So that's going to take a snapshot of the current time. Before we go any further in the loop, I want to take a look at what this, when the interrupt calls our have rotation. So let's come down here and look at our have rotation function. Now that we've taken a snapshot of our current time, when we get into this function, we are looking at, we're going to do if our current time minus previous time, our current millis minus previous millis, if that is greater than millis delay time that we have set for 5 milliseconds. So basically we're looking to see if 5 milliseconds has gone by. If that amount of time has gone by, then we go ahead and do the rest of what's in this function here. We're going to compare a digital read pin B. We're going to see if it's 1. If you remember from before, when we're turning the encoder clockwise, pin A is 0 or low and pin B is high. They're different, and that means we're going clockwise. That's exactly what's happening here. So the Arduino has already done an interrupt and detected that we have movement on pin A and it's low. So we come in here and we do a digital read of B. It's high. So we're going to go ahead and know that it's counterclockwise, and we're going to increment our encoder position. At the same time, the interrupt triggers pin A low. We get in here and we find out pin B is also low. Then we know that we are going counterclockwise, and we're going to decrement our encoder position. Then we need to move our current millis into our previous millis so we can compare it next time we loop through this. So in this line, we're just looking at the switch. We're going to do a digital read of the switch pin, and we're going to make sure nobody's pressing it. If somebody is pressing it, we're going to zero out the encoder. In our last version, we were comparing current state to previous state. In this version, the interrupt does that for us. So it's already made the change to our encoder and increased or decreased it. So what we're doing here is we're looking at encoder position to see if it is different than the previous encoder position. If it is, we're rotating, we're changing states. Now if we do change states, we drop into here, and this is where we're going to set a limit on it. So if the encoder position is greater than our high limit, then we're going to go ahead and just tell it to keep the high limit in there. So if it's higher than, in this particular case, we set it at 40. So if it goes higher than 40, we're just going to say it's equal to 40. Same thing down here. If it goes lower than our low, which is set at 0, just make it stay 0. Then down here, we're going to go ahead and put our information in on the serial monitor. We're going to say what the encoder position is and the direction. Then we're going to make our previous encoder position equal to our encoder position. Okay, on this line, we're going to do an analog write. We're going to write to the LED pin, and we're going to use the map function. What the map function does is it basically rescales a number from one range to a completely different range. So in our case, we're going to rescale our encoder position which we have a range going from our encoder low, or 0, to our encoder high, or 40. We need to take that 0 to 40 and make it 0 to 255. So 0 to 255 is going to be our pulse width modulation, which is how we are analog writing that number to create the brightness of our LED.
Okay, our encoder is currently set at 0. I'm going to go ahead and turn it clockwise to increase it. And you can see our LED is getting brighter and brighter, a little bit more intense, all the way up to 40. And we can go back down to dim it to 0. We can go halfway up, or anywhere actually. We can press it to 0 it out. So that's how we can dim an LED using a rotary encoder. For all those that stuck through this entire video, thank you. Hope you learned something. If you have, hit that subscribe button. I know this was kind of a long one, but there's kind of a lot to cover too. Some of it I felt like I could have gone further in depth, but I guess that's for another video. If you have any comments, please leave them down below. I'd love to hear from you guys. Anything that I can change or what we could have done differently in the code, let me know. I hope you guys all have a great day, and thanks again for watching.